So we finished with the scalar field, and now an example of gauge field theory. So Euclidean version, in the Euclidean version of Yang-Mills theory, space-time category, so let's say d-dimensional Yang-Mills. Space-time category is Riemannian, and in addition, one can make a choice of a principal G bundle. So throughout this discussion, G is a simple compact Lie group or U1. So that means objects are d-1 dimensional Riemannian manifolds with principal G bundles on them. Morphisms are d-dimensional Riemannian manifolds with principal G bundles on them. And when you have a morphism M between N1 and N2, then the restriction of the principal G bundle from M to N gives the principal bundle here. So the structures should agree, just as well as metrics agree. So we can choose all these bundles to be trivial. That's a canonical choice for in this case. And then pseudo-Riemannian, same thing. It's a pseudo-Riemannian category, but equipped with principal G bundles. So this, we will focus on the discussion on this case. Well, of course, physically, most interesting is this case, but in this case there are extra difficulties and things to discuss because of the pseudo-Riemannian nature of these manifolds. So just for simplicity, let's look at the simplest, well, at the Euclidean case. So, so this is the space-time. Fields are connections on this principal bundle G that we have over the space-time. And the action Yang-Mills action is the so what I'm discussing now is pure Yang-Mills without matter fields. It's the trace f of A dx.
Also known as the norm squared, I suppose.
But
also known as the norm squared of the curve.
yes. So let me just explain the notations. So here, trace is the killing form on the Lie algebra G of the Lie group G. So if EA is a linear basis in G, then that's the bilinear form. And then the so then we can write the I didn't say what is the curvature. The curvature. So F is the curvature of A. And these notations, so locally A is a one form, so I'll assume that A is a one form. So it's an element G. So these notations mean the following. We will write a G-valued form in the basis E. If we have another form, then A wedge B is sum over AB, Lie bracket with respect to the Lie algebra, and then the exterior product of forms. So this is the curvature of A. A is a connection, F is a two form. It's globally two form, this is only local. So then I think everything is clear. So this notation trace f of A simply means sum over AB, trace EA EB, and then FA scalar product FB with respect to the metric on M. So when you have a metric on the manifold, you have a natural scalar product on forms, and that's what it is. Okay, so this is the action. And then, just as in the previous cases, we can set Dirichlet boundary conditions. So for this, fix the connection B on the restriction of our principal G bundle to the boundary of M, and the Dirichlet boundary. So then we have the embedding of the boundary that pulls the connection A to the bundle on the boundary, and that's the Dirichlet boundary conditions. And plus Euler-Lagrange equations. That's the condition that the variation is 0. So that could give a good system of differential equations that could give a good boundary problem, but it doesn't. So that's the difference between the Young-Mills theory and the, say, nonlinear sigma model. That in the Young-Mills theory there is something that's called gauge invariance, and so the set of solutions to this boundary problem is not discrete. So what we have to do first is we have to sort of take into account the degeneracy of this functional, and this functional, in contrast to the scalar field, to the nonlinear sigma model, it's highly degenerate. So why is it degenerate? It's because there is an action of the gauge group. Gauge group, this is the group of bundle automorphisms of our principal G bundle T locally. acts locally, such gauge transformation is a map. Locally, I mean, we choose a neighborhood in M, then it's a map from U to G. Globally, it's just it's the bundle automorphism. So I think Ben discussed it in the Chern-Simons class. And locally, let's just for simplicity assume that G is a matrix group. So then the action of the gauge transformations on connections is given by this. So it's a matrix group. It means that it's a subgroup in n by n matrices. And so G-valued connections are also n by n matrices. So the adjoint action is really the conjugation of n by n matrices plus G inverse G. So this is how the forms would transform, and this is how connections transform. And this term comes from the fact that actually the connection is not a one form on M, it's a one form on the bundle of the form, locally of the form theta plus A, where theta is the Maurer-Cartan form on G. So this is the how the gauge group acts on connections. And then the curvature is the form, two form on M, so it transforms as forms transform. But then you can see that the Yang-Mills action, which unfortunately I erased here, it is invariant with respect to these transformations. So there is an infinite dimensional Lie group which acts on the infinite dimensional space of connections, and the action is invariant with respect to the action of this infinite dimensional group. So you can see that in particular critical points, generically critical points of this functional are not points. They are generically orbits of the gauge group. So the space of connections look like this. So generically, if we have a critical point here, then every point on this orbit will be critical. So in the space of connections, generically we have the whole critical orbits. So what's the morale of this? If we really want to have some kind of reasonable differential equations describing the classical dynamics of these fields, we should consider not the space of connections, but the space of connections modulo gauge transformations. In other words, kind of the real dynamics is happening in the space of orbits, not in the space of all connections. So, but once we will start to pass from the space of connections to the space of these equivalence classes, to this modular space, then we also should make sure that we set the boundary conditions, not for connections, but for equivalence classes. I don't want to do it now, I just want to proceed somehow, leaving this behind. We will have a discussion of this later. But I just want to emphasize that this is what happens in gauge theories. There is this invariance with respect to the infinite dimensional Lie group, and this is why the whole dynamics is somewhat more complicated. One has to pass either to this quotient space, and these quotient spaces are usually quite big. So, and how can we, practically speaking, sort of deal with quotient spaces? So, one way to do it is to kind of construct enough of invariant functions and to deal in terms of this with the problem in terms of these invariant functions. And the other way to deal with this is to choose a cross-section through the orbits. So then the cross-sections through the orbits will be exactly the quotient space, if it's really cross-section. So, but the quotient spaces are so bad that usually there are no good cross-sections. But nevertheless, let's not worry about typical topological problems of quotient spaces, and let's proceed anyway. And we'll see what happens. So this is the Yang-Mills theory. So if there would be no gauge invariance, there would be no difference with the previous cases. But because there is a gauge invariant, because this action is highly degenerate, somehow we have to pass to this space, or we have to do something equivalent. So that's all I wanted to say about the Yang-Mills theory for the time being. So then, any questions?
You write the symplexic structure?
I didn't.
Not
that,
symplexic, but the boundary term.
boundary term.
Or if
I can do it, but why don't we do it like this? Let's leave it as an exercise. So I mean, there should be exercises in this course. So if you can make a record of all the exercises that I suggest, that's the first.
What's the one about correcting sign in your formula?
First, right? What?
About correcting sign in your formula. There was an
In which
exercise.
Previous lecture. So,
Previous
so
lecture.
this is exercise 2, I guess.
Yes, I would make it more general. Correct all signs. So write explicitly the Fourier-Lagrange equations for the Yang-Mills theory and boundary terms in the variation of the action. It's a very straightforward exercise. I can do it, but it will be better if everybody will do it. So, any other questions? Okay, so then let's proceed to the next model. And well, I didn't plan to say this, but somehow now I feel that it's better to say something about not necessarily pure Yang-Mills theory. So let's say the Yang-Mills theory with method fields. Say a standard model that now is the candidate for all fundamental interactions except for the gravity, and that's the one that is tested in CERN, has the same structure. The structure of fields will be more complicated than in this example, but in principle it's the same thing. So now space-time is the same, Riemannian, with one extra structure. So it's Riemannian plus, remember that I said that space-times, they may have many structures. So Riemannian is the first structure. Then principal G bundle is the other structure. And then we will also have, say, some fiber bundle on which the with the G action with fiber-wise G action, but it doesn't have to be strictly transitive. So you can have some stabilizers. So this will be, so connections here are Young-Mills fields, and sections here are matter fields. So an example of such thing would be just simply, let's take P over G with some representation V, some finite dimensional representation of V, of G. So so then an example of such theory would be is the Young-Mills term plus the term describing the interaction of the matter fields with the Young-Mills theory. That would be 1/2 dA phi dA phi, and I assume that this space V has the G invariant scalar product. So dA is the covariant derivative with respect to A. Phi is this section of this bundle of matter fields, and the scalar product is the scalar product of forms plus the scalar product in V. So these are V valued scalar forms. The metric gives the scalar product of forms, and then the target values are taken with respect to the scalar product in V. So this is an example of the interaction of the Young-Mills theory with the matter field, plus possibly we can have some self-interaction of this scalar field phi.
But it's not exactly the theory of real life because you didn't include fermions.
No, of course, yes, I didn't include fermions. We didn't discuss yet what fermions are. We will discuss what fermions are, but in order to have realistic fermions, this structure is not enough. So if you want to include fermions in the theory, this is for those who knows what fermions are. If you want to include them in the relativistic invariant theory, then you have to fix a spin structure on Riemannian manifolds. So the space-time category is more complicated, a little bit more complicated. It's like it's not just Riemannian manifolds anymore. It's just Riemannian manifolds with spin structures. Once you have spin structures, you can sort of speak about sections of the spin bundle, and sections of the spin bundle are spinors, which usually sort of appear as fermions in theories with fermions.
But, sorry,
Yeah.
the scalar field in this case represents the Higgs boson?
Yeah, for example, could be, yes.
Yeah.
Mm-hmm. Again, so in this case, yeah, this is just an example. Things can be slightly more complicated, but roughly speaking, with the same structure. You use the covariant, so matter fields will always be sections of some fiber bundles on which the group act, and then you use the Young-Mills field you use the covariant derivative with this connection to construct such things, and that's usually the interaction. So Okay. So then a few words about Chern-Simons. We'll have to hold next week, hopefully, for the discussion of the Chern-Simons. So I want to start slowly. So before we'll pass to the Hamiltonian formulation of classical field theory, a few words about Chern-Simons. So the remarkable feature of Chern-Simons field theory is that it's a gauge theory. So it has all these ingredients of being degenerate, but the space-time category is much easier. It's a gauge theory on a topological space-time category. So it's a topological classical field theory in the sense that we don't need any metric in order to deal with this theory on spacetimes. And so I already said what is the so we'll focus on three-dimensional Chern-Simons. So the space-time category is topological, three-dimensional, and fields are connections on a trivial G bundle over M. And the bundle is trivial, so one can identify connections with one forms globally. And so the Chern-Simons action is integral over M trace A dA. Here's the next exercise. Check the sign. So I think it's correct. So notations are the same as before. It's the it's slightly different now. The difference is, and it should be 1/2. So the notations now trace of A wedge B. This is simply, again, if you, so all these connections are G valued. So for G valued, for two G valued forms A and B, we define this thing as sum over A B trace EA EB, and then AA B B, and then I also assume that G is a matrix group. So the Lie algebra is also a subalgebra in the Lie algebra of n by n matrices. So when I write trace A B C, this is simply trace EA EB EC, and then okay, so
Are you sure?
What?
About the last one, because it seems to me that you should put a commutator there, but maybe.
But if you have a matrix group, it's fine.
you know that's exactly what I said.
It's because of the 2/3 and minus signs on exercise 3.
Exercise 3, yes. Check,
Because
check whether
they're-
it's correct.
Okay.
So
So otherwise
what-
it would be 1/3 A with
Exactly.
1 and commutator.
yeah.
Okay.
I think it's positive. No?
Plus 2.
The conjecture is it's plus.
So that's clearly an
Do
excess.
you remember?
So,
That's my one.
so this is the action. Now let's look at its variation. So when we will vary, this term will produce the quadratic term in A, and one factor will be the variation of A. And because we can take a variation of this, or this, so this 1/3 will be cancelled. So here we will have the variation of this which dA, and then we also will have A which d variation of A. If you want to have just the variation of dA, we'll have to integrate by parts once. And so this will give the integral over the boundary. Trace. So here we should just use the Stokes theorem. So that would give us the pullback of the connection to the boundary, and then pullback of the variation of the connection to the boundary, minus the integral over m, trace. And then it's a simple exercise, which I think when you probably did it in the class, to see that the bulk term of the variation is simply given by this formula. And now you can see that Euler-Lagrange equations the curvature of f of A is 0. And then provided that the Euler-Lagrange equations are satisfied, the boundary variation is given by that integral, which should remind you the first order Lagrangian mechanics. Okay, so this is the so now the question is, how should we set the boundary conditions? Well, boundary conditions should be set in such a way that the restriction, and there is only one reasonable way to restrict a connection to the boundary, is just to take a pullback of the connection to the boundary. So this should belong to some submanifold. And as you correctly noticed during the last lecture, the only thing that's needed from this submanifold is that L should belong to the kernel. Well, let's see.
Section space.
Yes. So this thing, what appears here, it belongs to the tangent space to and this submanifold is the submanifold in the space of connections on the trivial G bundle over the boundary. So we have the space of connections on this bundle, boundary conditions should be the subspace in this space. Now, what's written here is the tangent vector to L at the point I star A. And so, what's written here can be thought as integral M raise I star A is the value of the one form alpha at the point I star A. On the tangent vector, this is the one form on L at this point. On the tangent vector, delta I star delta A. So it's just as in first order classical mechanics. This is the reason why I discussed first order classical mechanics, because it's a finite dimensional model for the Chern segments. So the only requirement is that this should be 0. In other words, L should be in the kernel of this form.
L should be an integral submanifold of the distribution gotten by the kernel alpha, right? So the tangent space to L should always be in the kernel alpha.
That's right. Tangent space. Of course, yes.
And then there's a boundary on M, the integration over M is
Over the boundary. Yes. Okay, so this is how we should set up the boundary conditions for the Chern segments theory. If we want really the extrema of the action to be solutions to Euler-Lagrange equations with certain boundary conditions. But then we have the same problem that up until this point everything is fine, but then we will have a problem of degeneracy of this action, because this action is actually gauge invariant. So remember we had this condition that the matrix omega ij should be non-degenerate. This is not the case here, if you write it in terms of matrix, of this matrix omega ij. So S Chern-Simons M is degenerate. And the reason is that this action is gauge invariant. Well, strictly speaking, almost gauge invariant. So what does this mean? It means the following, that if M is closed, then if we will do gauge transform on A, we will get the Chern-Simons action plus, with the appropriate coefficient, the integral over the boundary. The integral over M trace G inverse dg third power. And this is the
plus a boundary charge.
I assume
Oh,
that
M is
closed.
closed. That's
Yes.
right.
And this is a topological invariant, so it's just the degree of the map from. Well, this is an integer. Number, so it's equal to S Chern-Simons MA mod Z. So strictly speaking, not the action itself is invariant, but the exponent of the action is invariant. Its own integer coefficient. But that's enough to destroy the beautiful picture of first-order non-degenerate systems. And so we have to somehow, again, the morale is clear. So instead of the space of connections, where we have the gauge invariance of the action, and where the action is degenerate, we have to pass to the quotient space, H group. So we have to pass to this modular space, and then one can expect that things will improve, at least at a generic point. And so this is the this is basically what happens in these examples of classical Lagrangian field theories. We have non-degenerate second-order classical mechanics. We have non-degenerate. We had an example of non-degenerate first-order classical mechanics. We had an example of second-order non-degenerate classical field theory. That's the scalar field or nonlinear sigma models. But then we have two examples of gauge theories where the actions are degenerate and where, in order to speak about something sensible, we have to pass to these quotient spaces, or we have to do something equivalent to passing to these quotient spaces. But these are the theories that we want to study, so this will be the goal. So far we discussed the Lagrangian version of classical field theories. In order to have the complete set of tools to deal with these problems, we also have to have the Hamiltonian formulation of classical field theory. And we had bits and pieces of it when we discussed first-order Lagrangian systems, because we already had the Hamiltonian structure there at the Lagrangian level. So now we'll make a switch the gears. So now the next subject is the Hamiltonian field theory. Any questions about the Lagrangian approach?
Can we maybe digest it over coffee?
Yes.
For half
So it's a digestive break.
How long for half an hour?
an hour.